All right. So I am online. If you guys ever played StarCraft, that's one of the lines of the Goliath. Um, Goliath Online with the proper sound effects. I don't have those sound effects here. Um, so this is kind of the plan for today. Exam 2 is done. I'm done grading it. I still have some more clerical work to do, so during the lab time today, I might be able to finish all of that and be able to update the scores on Canvas. So that's my current plan. The lab for today, yes, there's lab for today. So the lab stuff for today is kind of self-contained instructions, but I'm going to go over some of that stuff in class today. So I just wanted to point out, I know, this is before the class starts, but if you're here already, I just want you to remember that the labs are not exactly just quote unquote labs where you just kind of breeze through all the instructions, get a certain sequence of actions done, and you're okay. The labs actually contain instructional material, so that means you might want to jot down some notes as you go through the lab stuff, because that actually contains instructions and knowledge and skills that you might need, for the completion of this class. I also include the link of today's lecture notes. I'm not really sure how far we can get into the lecture notes. It is once again orthogonal to what the lab is doing, so I'm going to go over the lab stuff first, just so that you guys have some background knowledge of how to get the lab stuff done. And we got we're going to text in. What is the plan regarding Thanksgiving? We're going to miss that Thursday. So we're going to miss another day in the semester. I understand the importance of Thanksgiving to a lot of people, so I'm not trying to downplay the importance of Thanksgiving. However, from the perspective of this class, in terms of how much material I can go over, that's another day off, for this class. So we lost 2 days already, because of last Thursday and then um, Thanksgiving Day. Well, the good thing is we're not taking the entire week off like high schools, so at least we got next Tuesday. Still you'll be able to cover some material in the lecture. The difficult part is the continuity because I think that's going to be the part where I'm most concerned about is the continuity because next Tuesday, from next Tuesday, the next lecture is going to be a week later. So it's kind of like the situation from last Thursday, right? And the lack of continuity can potentially be a problem. Okay, I'll take it back. I will say definitely going to be a problem for some people. So I'll try to mitigate that effect by giving you guys something to do, over the really, really long weekend between, so, as soon as you recover from food coma, you can do some of those things that I'll give you to do next week. Oh yeah, yeah, the unofficial homework. Yes, we'll definitely go over that. That's a good idea. All right, so we got 2 seconds to go, and now we are right there. Okay, cool. So the first thing I want to do is to go over, as Jonathan reminded me, because if he did not, I would have forgotten about the ungraded assignment that I gave you guys, from last week. All right, so I'm really hoping everybody got a chance to, kind of work on it, because I can almost say for certain, people who do not spend any time to work on that, um, it's going to feel the effect. I'll just put it that way. Um, because, I put those items here, for a very specific reason. Basically, I want you guys to think about all the things that we have already introduced regarding how we use the stack, how we call a subroutine, and so on. So the answer, the question is, how do we get all of these things understood? Understanding the sentences word by word is not understanding the concepts. Okay, so understanding the concepts means you have enough knowledge that is represented in a non-verbal way in your mind to the point where you can use that knowledge to troubleshoot and apply those kinds of knowledge to to basically answer your questions that I might ask in the final exam. And no, I am not going to teach to the exam. Okay, so that's not going to happen. All right, so but I will teach, okay, to the point where hopefully all of you will get the knowledge that you'll get a reasonable score in the final exam. Okay, um, nothing will make me happier than the entire class getting A's. Okay, but you know that's but I cannot do that by giving free points. So so that's going to be, so people have to demonstrate that they fully understand the concepts in the final exam to do that. Okay, so hopefully people have some time to review this particular thing. So here is the program. So if you go there, go to this link here. It is a very simple program, and I make use of online GDB. So this way, you can actually play with this program if you want to. Save it in your own folder. It's not a very complex program, right? I mean, you have main calling G, G in return calls F. F doesn't do a single thing, returns back to G. G then returns back to main, and then main itself is going to call F, right? So F returns back to main, and we are all done with this program. So in terms of the call return behavior of this program from the perspective of C, this is pretty simple. Now from here on, I'm just going to say C instead of C++ because C is for the most part a subset of C++. So when I say C, it is actually a part of C++ that you should have learned already. So that's kind of, because this really is just straight C. Okay, if I start to use classes and object-oriented programming, then I would use the term C++. Okay, but this is just regular C. All right, so moving ahead, and we want to answer some of these questions. So do I know what instruction does? Okay, let me first translate this code into TTP ASM assembly language. You can use the module used in class to help. Be sure to start with a no-op instruction at the end of the main with a halt instruction. So basically it is, for the most part, copy and paste from what we talked about the other day. You just have to kind of invent the names of a whole bunch of labels. So in today's lecture, I'm going to show you guys how you do not need to use labels to mark the places where a subroutine is supposed to return to. So we'll talk about that. And then next, run the assembled code, object code, opcode as downloaded from the RAM file tab. You can do this in Logisim GUI mode first, and then ask yourself these questions. So I'm not sure whether you guys want me to go over the actual assembly code or not. So let me know. Okay, so we got a yes. Okay, very good. I'm just gonna go find a terminal where it's the right size. There we go. All right. Oh, this is how I install Joplin, on my system. Not that it is of any significance, for this class. All right. All right, so what we would do is, what I typically do is I would look at the C code on one side and look at the assembly code on the other side. And for this one, it's easier because I can just make the text window a little bit smaller and then display the C code on this side and then overlay my terminal on the other side, just like that. Alright, so I am going to use NVim. Once again, this is just my editor of choice. You can definitely choose whatever you want to use, like Notepad in Windows, Notepad++ if you want to install that, and so on and so forth. Alright, so this is going to be, I would just call it another call return.ttp-asm. That's the extension that I choose to use, for the file that contains all the mnemonics of an assembly language file. And here we go. So I will start with a no-op instruction, and you can see my editor actually has syntax highlighting built into it, and that is customized to TTP-ASM. It's a convenience feature. You don't need syntax highlighting to get things to work, but having syntax highlighting definitely helps me locate problems before they get out of hand. All right, so this is kind of the shell. I just want to jump to main from the first part of the program, because otherwise it would just kind of fall through the whole thing. And I want the ordering of the definition of the subroutines to be the same as the definition of the subroutines in C. So that way, it's easier to locate, which function is which function. So now we'll deal with F first. F doesn't do a single thing, so that means we are going to return right away. So this is the important part. This is actually relevant to what we are going to do today to a certain point. When a subroutine, a called subroutine, which has the name of a callee in this case. So from the callee's perspective, at the very entry point, the one thing it can assume, at least at this point, is the stack pointer points to somewhere in memory where the return address is located. So, but otherwise, there's nothing that the callee can assume, not whatever is in the register except for the stack pointer. So registers A, B, and C, we can make no assumptions whatsoever in the callee. So that means I can, the only thing I can reliably do in order to get the return address into a register is to do a pop sequence. Uh-oh. I hope you guys didn't see the blackout, because I just got a very short amount of blackout on my screen. I think it's still streaming. Okay, yep. Okay, so I can, let me close my browser so it doesn't take up unnecessary resources. All right, so we use this instruction to retrieve whatever item that the stack pointer is pointing to into register A. And this is just a reminder, if you do not know what LD is doing or how it is getting it done in the processor, you might have some catching up to do in this class. Okay, so the next thing to do is to say, okay, this location is no longer useful to us, so we're going to reclaim that location so that we can use it later on for something else. So instead of quote unquote, getting rid of that location, we cannot do that. Okay, that location is always going to be there. So we're moving a bookmark instead. The bookmark is the stack pointer, which is register D. By changing register D by changing it to be one more than what it used to be, we are now saying, this location can now be reused later on. And then at this point, we can do a JMP-A, because I put the return address into register A. And JMP-A is basically just like PC equals to register A. So whatever content we have in register A becomes the location where we're going to grab the next instruction. That's how we return from subroutine F. So from the perspective of subroutine G, it's kind of the same deal, but except it cannot return right away. It has to call F first according to the C code. So here is where we can use a non-label way to specify where we're going to return things to. So I'm going to explain that. If you don't like this format, you don't have to use it in your own program. But if you find it to be convenient, you can go ahead and use it in your own program. So the first thing we need to do is to this part is up to you, okay, whether you want to decrement D first or not. Because what we need to do is to push the return address back to G on the stack before we call F. So to allocate a byte on the stack and say, okay, we're going to need this location to store something is a decrement D, because increment is to deallocate, and that makes decrement to allocate. So now, after the decrement, whatever the stack pointer is pointing to is now quote unquote reserved, but we haven't really put a meaningful value into that location just yet. So this is how we're going to do it, and we don't have to use register A. Feel free to use register B or register C, because registers A, B, and C really do not have any special meanings. Until we get to return values, okay? But we are not there yet, okay? So don't worry about return values, and registers A, B, and C are basically, they're all generic registers. So now I'm going to use this notation here, okay? .5+. So I'll explain that later, okay? So right now we are just going to say that's kind of strange, but I'm going to claim that .5+ is specifying, the location where the subroutine is supposed to get back to. Okay, so I'll explain that in just a little bit. So now we have as std b. Once again, you really should know what is LDI, what is LD, what is ST at this point of time, and also understand how the processor internally gets it done. So right here we have pushed the return address already, and then we're going to use a JMPI to unconditionally continue execution in function f. So that will continue execution in function f. So normally we're going to use this location here to specify where call f is supposed to return to. But this time we are not going to use a label, okay, because this is going to calculate that. So we'll go ahead and say now it is function g's own term to return. So we're going to use almost exactly. So I just like to play around with different registers. So this time I'm going to use register C. There's nothing that says you have to use register A or B or C. So I can use register C. This time I just have to be consistent. So increment D, and when I say consistent, it is the consistency between the LD instruction and the JMP instruction, not JMPI, okay, just JMP. Alright, so that is function G, and then main has one job to do first, which is to initialize the stack pointer. And then you can call G, and then you can call F. Okay. Now the nice thing about using .5+, using this approach here, on this line here, okay, let me turn on line numbers. So the nice thing about line 11 is now I can copy and paste without any worries that it's not going to work, because I'm not relying on additional labels to tell me or to tell the subroutine where to return to. It is all relative to the dot notation. So I'll explain that in just a little bit. So I am just going to copy from line 10 to line I would say 14, but line 13 is all we need to over here. To this current line, which is a dot. And did I do that? No, I did not, because I have to copy over here. So let me try it one more time. So we say copy line 10 to line 13 to where I am. Nope, that doesn't. Gosh, I cannot believe that I forgot how to do copying in VI. Alright, so this always works, yank and then paste. Alright, but this time we are not calling F, we're calling G, right? So right there, change F to G. And now I can just copy these 4 lines into here, and this time I'm calling F. There we go. Alrighty. Alright, so now let's go back and figure out what is the .5+. Okay, so the first thing we need to do is to go back to not this. I'm going to open a new tab because I don't want to lose track of the ungraded assignment. So I want to get back to shared folder. Great. Yes, I forgot about that link issue. We'll see. I thought I changed it, but it won't open it inside that box. Alright, so we go to processor, and then in the assembler manual it explains what a dot is and what is postfix notation. So this is one resource you can go to kind of figure out what that expression is trying to express, or what is the value of that expression. And right here, so we're gonna use right here, label definition and postfix expressions. So read this section here if you want to understand postfix notation. I'm not sure whether I put the dot notation in here or not. I might have forgotten, or might have changed it and then not to update the document. Doesn't seem like it's here. Okay, that's okay. We can go back to here. Alright, so the dot notation, okay, so let me go back to line 11. The dot notation here, this dot here, it should be there. Okay, I'm suspecting it's there. But the dot simply means it is the location of the LDI opcode. So the opcode of the line that the dot is belonging to, that is what the dot is denoting. Now you might say, but where is it actually? Well, we won't know until the assembler actually get to this line. Okay, so the assembler is the one that has to figure out what dot really is, in the assembling process. So because this is a postfix notation, so that means I'm pushing the dot, which is the address of the LDI instruction opcode. I'm pushing the value of 5 on the stack, and then the plus, which is an operator, is going to pop 2 items from the stack and then add those 2 items. So this is why it's called postfix notation, because we are used to an infix notation because we put an operator between the values that it is supposed to operate on. But the postfix notation is saying, okay, you have to give me the values first and then tell me what to do with the values. And postfix notation is closely related to the concept of a stack, because every time you specify a value, it is pushed on the stack. Every time you perform an operation, it will be popping a number of items from the stack, perform the operation, and then the result of the operation is also pushed back onto the stack. So it's a very neat and easy way to specify expressions, except it is very foreign to us because we have been poisoned by infix notation, where the operator is between the values. And even when we started to program, we have also been poisoned by prefix notation, because when you call a function, the name of the function that specifies what to do is before the parameter, before the arguments. So it is basically essentially a prefix notation. So we have a lot of exposures to infix notation. We have some exposure to prefix notation, but what really makes a lot of sense is postfix notation, because in postfix notation there is no need to use parentheses. But that's a whole different topic for another day, so I'm not going to get too much into it. So the question now is, why are we adding 5 to the address of the LDI instruction? So this is how we do the counting here. So in this particular instruction, okay, slash starts comment, not pound, we have offset 0 being the LDI opcode itself, and then we have offset 1 from the dot notation to be the return address, okay, to be computed. Okay, so that's the very same thing that we're trying to compute here. This is only taking up 1 byte, okay, so this only taking a 1 byte, so it will be at location, oh, I shouldn't say it. So offset 0, offset 1, this is offset 2. JMPIF is going to take up 2 bytes, right? So it's going to take up offset 3 and offset 4. So offset 5 is actually the address of the LD instruction, which is the first instruction we should execute after function f returns. So it actually gives us exactly the same as if we were using a label, except in this case we are not using a label, which also means copying and pasting is going to be a whole lot easier, because we don't have to copy and paste and then change the label to a unique name. And we have to change both the definition of the return address label and also the reference to the return address label, both. If we change only one of them, it's not going to work. All right, so do we have any questions about this part? So there are 2 main concepts here. One is the postfix notation. Dot 5 plus means dot plus 5. Okay. The second concept is what the dot is representing. The dot is representing the address of the opcode of the same line where the dot is located. So we are talking about, in this case, the address of the opcode of the LDI instruction. We are not going to it's not the address of the constant, which is dot 5 plus itself. It is the address of the opcode itself. All right, so we got some questions coming. So 5 is representing the number of bytes. Yes, it is basically the number of bytes from the LDI instruction itself to where function f is supposed to return to. So Jonathan is correct about that. Yeah, I thought so. This is, by the way, a feature that I added after I have to create labels all over the place and go like, no, that doesn't make sense. Let me do something that's a little bit better. So there we go. And I thought Richard had was typing a little earlier. Maybe. Okay, that's okay. All right, so and the nice thing is we can just copy and paste this all over the place. So are we doing okay so far with the program? Okay, we got one confirmation. We got two. Does anyone have any question or need more time to kind of absorb this information? All right, I'm not seeing anything. All right, well, since the whole thing is being recorded, I am going to continue with this thing here. And the next thing I'm going to do is going to use River Spider, which is basically just a script, okay? So I will show you, how that works. Okay, so let me go back to the folder where the tool is installed. Okay. All right, so you have to get into the folder first. And the nice thing is once we're in that folder, I just have to run a shell script. This is a bash script. And then supply the path to the TTP ASM file, the assembly source file. So that is located in my temp folder. It is called call return.ttp ASM. And then I just have to press the enter key. It's going to submit it to the assembler, which is a Google spreadsheet. It's going to get the object code, check whether the object code is good or not, run the simulator on command line, collect the trace from the simulator, and then submit the log of the trace back up to the assembler for it to be analyzed, so that by the time we get back to the assembler, which is where? Oh, I haven't even opened it yet. Okay, there we go. So we're going to open it. So by the time we open it, everything is done already. Okay, so this is like one command to do everything. So here is the program. I did not type the program into the assembler, but it was uploaded by the script. The RAM file contains the assembled object code. So they are basically all hexadecimal digits, basically specifying all the bit patterns that need to go into RAM. The trace raw data is automatically uploaded as well, so I don't have to remember, so which one do we need to click here? Because remember, we got three options. We have to replace the current sheet, we have to use the tab as the separator, and then we have to turn off the automatic conversion between numbers from the TSV file and the representation in the spreadsheet. I don't have to do a single thing. This is all done automatically. So the analysis is now also more concise. You can see most of the empty lines are gone. And that is thanks to the upload interface. It automatically print all the empty lines. So the trace itself is a little bit more concise. It has exactly the same information. It just looks a little bit better than to doing it by hand. Okay, so but the point is, okay, we got a few questions to answer, right? Because let's go back to the question that we need to answer. All right, so do I know what each instruction does? Okay, so let me go back to the source code first, and then we can take a look at those instructions. So nvims temp call return.ttp asm. So the question is really looking at all the instructions, and I'm asking, do I know how every single instruction works in this case? Because if I do not, then I probably want to spend some time to figure out, how they work. At least to the point that I understand, not maybe not, okay, internally how the pathways are established, which multiplexer is switching which input to to the output. Maybe I don't need to go all the way down to that detail, but I do need to know what is happening to like in the ST instruction, okay, which one is the pointer pointing to the location? Are we reading from RAM or are we writing to RAM? What are we writing to RAM? Okay, how do we specify what we are writing to RAM? We need to answer all of those questions. Okay, so from the perspective of actual assembly language programming, not even knowing what the processor itself, how the processor gets it done, we need to understand, how the registers are being used and what the instruction is really doing with the registers. Okay, so that's the first question. Next question, do I know what push and pop mean for stack operation? All right, so in here we have some pop operation. This is a pop operation here. and then we also have some push operation. So technically the push operation is the decrement D and the std instruction. This one thing here that is stuck in between is really not a part of the, well, okay, it depends on how you look at it. Okay, it does specify what value we are pushing on the stack, but it really has nothing to do with the stack operation itself. So when it comes to the stack operation, because register D is the stack pointer, so this one counts and this one counts as well, because we are using register D, the stack pointer, and we are dereferencing it so that we know where to store the value of register B. All this instruction is doing is to initialize register B so that we specify, oh, by the way, we are trying to push the return address, and this is how we compute it. So whether the LDI is really considered a part of the push is kind of debatable, but the decrement and the ST definitely are a part of the push operation. Okay, what about, so we talked about push, we talked about pop, and then this is a particular question here. Okay, so to answer this question, okay, let me answer this question first. Okay, so I'm gonna copy and paste it into Joplin. Then we can answer the question in Joplin. I figured out a lot of things about Joplin over the weekend and also yesterday, so I figured out that it actually is quite useful. There are a lot of interesting things you can do. Let's see. Let's see if I can just paste it here. Nope. Okay. Um, hmm. That presents a little bit of a challenge. Okay, Control C, and then go back here. And since I'm already in insert mode, let's see if I can paste. Yep, there we go. Excellent. All right, so we're going to answer this question. And what you want to do is to kind of keep track of the content of the stack kind of mentally. So when I push, so we'll just use one line to represent the state of the stack at any point of this entire sequence of operations. So the first thing is the stack is empty. Okay. And then we have one item on the stack, which is the value of 4. And then we have 4 and then 3. And then we have 4. But then we pop we pop to x1. So that means 3 is going into x1. Okay, so we are basically now saying x1 is 3 at this point. And I'm going to use double equal because, well, maybe single equal, because we are changing the value of x1, by popping 3 into it. And unfortunately, parentheses are interpreted, oh, maybe not. So I just need to scroll down here. Okay, so 3 is no longer on the stack. So when we push 2 on the stack, then 4, 2 are the items that we have on the stack at that point. And then we push 5, so we have 4, 2, 5 on the stack. And then we push 6, so we have 4, 2, 5, 6 on the stack at that point. And then we pop to x2. Okay, so what value do we pop into x2? It'll be the last item that we push on the stack, which is the value of 6. So x2 is getting the value of 6 here. But we only have 3 items left on the stack at this point. The next one is popped into x3. So we will have 2 items left on the stack, 4 and 2. And then x3 is going to get the value of 5. And then we're going to pop again. So this time it's the value of 2. It is popped into x4. So x4 is going to end up with the value of 2. And after everything is done, we have one leftover item, which is 4 on the stack. So that would be the answer to that specific question. And I'm just basically playing out every single stack operation. So the state of the stack is each line, each item, list item here, okay, that's the technical term in HTML. So each list item is essentially representing the state of the entire stack, and the stack pointer is always pointing to the item that is the rightmost in this particular notation. Whew, okay, so let's see if we got any questions. All right. No questions. but Matt is typing, so I'm gonna wait a little bit here. All right, so there you go. So each pop will take the last known value pushed. Is it always like that? So when we pop, we are always popping from what we call the top of the stack, which in this representation is the rightmost item on the stack. So the rightmost item on the stack is called, quote unquote, the top of the stack. And when we pop, we are always looking at the top of the stack and just pop it. So think about going to a buffet place. Okay, so when you go to a buffet place, remember the stack of dishes, that they put next to the food. So we are putting a dish, with a label of 4, and then we push another plate with a value of 3, and then a customer comes to take, whatever is on top of the entire stack. That would be the plate with a label of 3, and then we push another plate with a label of 2, another one with a label of 5, another one with a label of 6. A customer comes, so the second customer is going to get the plate with a label of 6, and then whoever is after the customer is going to get the plate with a number of 5, and then whatever is next after that is going to get the plate with a label of 2. And at the very end, we have one plate left on the stack, which is the one with a label of 4. So that's one way to kind of visualize how a stack operates, but using kind of more or less real life experience. Now, I do not recommend anyone to kind of put labels on those plates when you go to a buffet place, and just tell the restaurant owner that I'm trying to understand how the stack operates, and that's why I'm messing around with your plates, putting some labels on the plates. So that may not be a very good idea. However, you can go through this as a mind exercise, okay, and nobody can say no to that. No, queues are entirely different. Queues are first in, first out. So they are similar in the sense that we have a particular way, we have a structure to determine, how we put items into a container and how we get items out of the container. So from that perspective, push is kind of like, and queue, or put something into a queue, and then pop is sort of like dequeue, which is removing something from a queue. So they are basically we call these abstract operations. Okay, if you think about object-oriented programming, these are methods. So we have a method to put items into a container. We have a method to get items out of a container. From that perspective, these terms are comparable. However, from the perspective of the ordering, they would be not comparable, because a queue and dequeue, they use first in, first out, and then push and pop, they use last in, first out. So from that perspective, they are in a way opposite to each other. So there you go. Yeah, exactly. It's not just the shelves, refrigerators too. That's why at the very back from the refrigerator, most people have a mold farm. Oh, let's call it mold garden, because it's usually multicolor. So it's a mold garden at the very back, because the item that you bought like 3 years ago, it's still sitting in the back of the refrigerator because it's last in, first out. So whenever you go to the refrigerator to try to grab something to eat, you're grabbing whatever you just bought. Okay, and the stuff all the way to the back never get touched. Yeah, there you go. And interestingly, U-Haul trucks are also LIFOs, last in, first outs. That is funny. Stacks. That is funny. Very good. Very good. All right. So I think these are all very important questions to think about, okay, to ponder upon, because that is how we gain a better understanding, by doing stuff and relating it with other things. All right, so the behavior of the C code, we kind of talked about that already. How do you check the behavior of the C code? That would be like super duper easy, right? You just go here, and then you just step through. When you run the program, just step through it using the debugger. Okay, just use single step. Use the command S, or you can also use the user interface. That's a way to do it too. So that's how you check out the C code and how it gets it done. How do I check the behavior of the TTP version? Oh, that's even easier, right? You just go to the assembler, go to the analysis tab. Even if you have to do this manually, it just looks a little bit more bloated because of all the empty lines, but it will have exactly the same content here. So between the analysis tab and also the assemble tab, okay, you would know everything, because the analysis tab at this point does not really correspond the addresses to labels that we know. Okay, I probably can add a feature in the future, but not yet. Okay, so if you ever ask, okay, but what exactly is 0f? Because I can see it's jumping from location 1 to location F. What does that mean to go to location F? Then you have to go back to the Assemble tab, use column W, because it's in hexadecimal, to go to location 0f and say, oh, so that turns out to be the first instruction in main. So that part you kind of have to do it by hand, but for the most part, you can get through the entire code and figure out, how the control flows within this program. Okay, we get to main first, main goes to G, G gets to F, F goes back into G, then G goes back to main, and then main calls F again, F then goes back to main, get to the halt instruction at the very end, and we're done. Okay. All right. So getting back to here. Alright, so now we are asking how much stack space is used. Okay, so the first thing is, can I figure it out without using the trace analyzer or even Logisim? And the answer is yes. Okay, you really should be able to do it because you can count, right? Because main is going to call, every time you call a subroutine, it uses up 1 byte on the stack. So the question is, what is the deepest call that we have in this entire program? So main calls G, G calls F, so the maximum is only 2 levels. So that means we are using up to 2 locations on the stack only in this program. So Jonathan W is correct in the text channel. So the next one is, how do we double check that? Okay, how do we know that really is true? So we just have to keep an eye on register D and see how far it goes. And we can see it went all the way down to, this is FF, this is FE, and it never went below FE. It started off as 00, it got down to FE, so when you count the number of bytes in between location 00 and FE, there are exactly 2 locations. So that's the confirmation that we are only using up to 2 bytes on the stack in this case. Yep, because 00 is really just another way to say 256, because everything is mod 256 when we only have 8 bits to represent stuff. Okay, so what do we go from here? How do I know how to correlate the trace analyzer with the assemble tab so I know at which point which instruction executes? So you can go both ways in this case. Okay, so if you go to the assemble tab, you pick a particular instruction, let's say this one over here, which is at location 0D, and you ask, in the trace, when do we get to this point? Okay, then you're looking for location 0D in column A in the analysis. Okay, so here we have 0D. I just picked one that so happened to be within view, but you can also use a search feature. I think it's Control G to activate the search feature. You can also, if you can also go to Edit and then just go to Find and Replace, and that will give you a lot of options. We are not going to replace anything, but you can certainly find something. And you can limit it within a certain range. So you can say, I want to limit to a specific range. And if you know how to work with a spreadsheet, you can basically, you know how to specify this. So if you want to limit the range to say column A and not any other columns, this is how you specify the entire column A. And then you can just say, I want to find 0D. You can specify whether it's case sensitive or not. You can also use regular expression, which is very, very helpful at some point in time. But right now, if my only interest is location 0D, this is how I specify it, and then just go for search. So it finds one and find again. it should not be able to find another one. It says right here, no more results found, looping around. So that means there's only one occurrence of 0D of the entire trace in column A. So that's handy, okay, because you can use tools to help you locate things. If you learn how to do Google scripting, you can go to tools and then go to script editor, and you can extend the functionality of the analysis tab here. But even if you don't want to mess around with Google Script, it's still pretty easy. I mean, you just go to edit and then you just click on, search and replace, find and replace, which is Control H. So I lied. It is not Control G, it's Control H to pop up that particular dialog box. Technically, I did not lie because I did not intentionally try to deceive. I just did not know at the time whether it's Control G or Control H. All right, so getting on to. So if so, can I follow the execution of the entire program? Yes. Can I identify stack-related operations? Anything that involves register D is a stack-related operation. Can I relate the stack-related operation to the calling and returning from a subroutine? So that is a basically it's asking, can you map what you see in the trace in the assembler to the behavior that the C program is doing? Because that's what we're going to do now, is we are looking at C program and we're trying to specify the instruction in TTP ASM so that the behavior is replicated on our tiny little toy processor. What can a callee assume from a caller? So what can we assume about registers? The only register that is being shared is the stack pointer. Everything else cannot be assumed. In other words, the callee cannot assume any specific content in registers A, B, or C, and the caller cannot make any assumptions either. Okay, but at this point, okay, because we're going to get to a point where we will talk about a return value, and we go like, oh, so these registers have some special meaning in certain contexts after all. But at this point, they do not. Can a callee assume the meaning and context of what the stack pointer points to at the entry point of a callee? And the answer is yes. So the assumption is at the entry point of a callee, the stack pointer always points to the saved return address on the stack. What can a caller assume about the stack or stack pointer as soon as a callee returns? Who is responsible to dispose of the return address? The answer is the callee. Okay, and what is the value of the stack pointer when the callee returns to the caller relative to right before the JMP-I to continue execution in the callee? So the answer is you can expect the stack pointer to be one more than plus is a plus one. I'm confused. Is the callee the thing that is being called? Yes, that is true. Because it's just a generalization. When we use the EE, we are referring the person who's having an action performed on. So that would be the object in the sentence instead of the subject. So the doer has an ER as a suffix, and then the I guess you can go with doe is the one that has the suffix of ee, typically in English. All right, so that's it. It took up a good amount of time already. All right, so I think we only have enough time to go over the material so that you have an introduction of today's lab, so that the lab does not come as something that's like, we didn't talk about this. Well, even though the lab actually does contain its own instructions, I'm going to do something to help you understand those concepts here. Okay, so the lab that we are going to do today, oh, wrong class, never mind. And where is it? Oh, I guess, I just have to back up here. All right, so the lab that we're going to do today is going to deal with return values. So we should understand how to call and how to return from a subroutine. So the next thing that we want to talk about is how do we specify a return value, and that would be the focus or one of the focuses of today's lab. So today's lab is It's not stack operation. We got that done already. So today's lab is parameters and return values. So this is today's lab. So it talks about parameters and it talks about return values. So we are going to use a simple C program. Okay, so we're going to use a new program first. So let me see, create a new project. And it's going to be a fairly simple program. And we'll just go ahead and specify int f. And all it does, okay, is to return a value of 5. And we are not going to do a single thing about it in main, but we're going to call f. Like that. Now that is perfectly legitimate, even though it makes the program really kind of meaningless, but it is legitimate. Okay, so the question is, how do we return a value of 5 in assembly code? Well, it's not just TTP-SM. Okay, the general approach of a subroutine returning what we call a scalar, S-C-A-L-A-R, okay, scalar, which is basically something that can be represented by a native register. Okay, using a single register, we can represent that value. So that would include, in the case of the 686 instruction set, that would include most of the integer types, all the way up to 64-bit integers. It would include doubles, it would include floats, it would include pointers. But it would not include arrays, it would not include structures, it would not include objects. So that's kind of where we draw the boundary between what is a scalar and what is not a scalar. So all the numerical values are scalars. True, false, Boolean stuff, those are scalars. Pointers are scalars. Strings is interesting because when we talk about a string in C and C++, it really is a pointer to an array of chars, and because it is a pointer, it is also a scalar. So when the caller needs to return a value, it just has to designate a specific register as the one that will specify the return value. In the case of the 686 architecture, I believe it is register A. Okay, so the 32-bit version is called EAX. I cannot remember the prefix of the 64-bit version, but it's still register A. Okay, and in the TTP-SM, I'm just using exactly the same convention. I'm using register A to specify the return value when we return from a subroutine. So for something like this, okay, so if I go back to my editor here. So for something like this, I'm going to call this one return value. Okay. So we'll write this code. Okay. No op jmpi to main. And then we have function f here. So the first thing function f has to do in this case is the only thing it has to do, which is to return a value of 5. And that is as simple as that. Now this time it has to be register A because it is an agreement between the caller and the callee that register A is being used to specify the return value. And in this class, okay, we are using the convention of register A is the one being used to specify a return value. And then after this, it is the usual return code. Okay, so the usual return code is something like this: increment D and then JMPA. And somebody's going to scream. I'm waiting for someone to scream in the text channel. They'll go like, "Attack! You are just overwriting the return value because because once we execute the LD instruction, it's not going to be 5 anymore." I was kind of waiting for someone to point out this is not going to work. And that person would have been right. This is not going to work. So this is why when a subroutine has a return value, you can no longer use register A to store the return address. You have to pick one of the other two registers, which would be register B or register C. Now between those two, there's no significant differences. So you can pick one, just have to be consistent with that. So main doesn't have anything else to do. It's initializing the stack pointer, and then it's going to do the call. So this time I'm going to do another sequence. So this time I'm going to do, I'm initializing register A first, and because we are now reordering the instructions, it is now 6 bytes away from where the subroutine is supposed to return to, because the decrement is after the LDI now. And that's why we have to include the 1 byte being used by the decrement D instruction in this case. Then we have stdajmpi to F, and then when we get back, we'll be at the halt instruction, and it's time to stop the entire program. That's all. So this code here in C is equivalent to this code here in TTP ASM. And the only tricky concept, well, okay, there are one new concept and one kind of tricky concept. The new concept is here. This is how we return a value of 5. We simply say whatever value we're supposed to return, stash it into register A before we return from the callee. And then the other one that is kind of tricky is because I exchanged the ordering between the LDI and the decrement D instruction. So now the offset to the location where the callee is supposed to return to is 1 byte more, because now we have to also specify the decrement instruction itself as a part of the instructions between the LDI instruction and where the callee is supposed to return to. Are we doing okay so far? In terms of understanding how to use how to specify a return value. In this case, it's really simple because there's no calculation involved, and as a result, there's no calculation involved here either. Any questions? Are we pondering on how to return a value of 5, or are we pondering on why this is 6 instead of 5?
Can you hear me?
Yes, I can.
Okay, because like I was trying to type, but it's not sending it for some reason. I don't know if it's affecting everyone else.
All right, that might be, it could be my computer, but I can hear you. Yeah, go
Okay,
ahead.
at least this part works, but I'm good right now. So that's just what I wanted to say.
Oh, okay, thank you. All right, I'm just going to type something here just to test. Test, there we go. It appears in red instead of the usual kind of grayish color.
If it appears in red, it means it's not sending.
Okay. That's interesting because it's unusual to have the voice channel still working and then the text channel not working. Your server is out of sync with your server template. Sync template. No, I don't want to do that. But I can check. Okay, let me go back and check to see if I accidentally turn off something in the server. So give me a little bit of time here. Alright, so student role. But I cannot type either, so it's not just the permission of the student role, which is kind of odd. Yep, the permissions are fine. Everybody should be able to send messages, except the text channel is not working. All right, I'm gonna restart. Oh, okay, I can see Alexander is typing. Yep, that's working. So how is it returning the value of 5? Well, whatever value we want to return, we put it into register A. That's how we return the value of 5. There you go. What if we don't exchange register D? It's going to be 5 bytes if we don't exchange it, because that's what we did last time. So we just have to do some counting here, right? So we're just looking at offsets 0 and 1 in here. This would be at offset 2. This would be at offset 3. This would be at offset 4 and 5. So that makes the halt instruction at offset 6 from the LDI instruction. So that would be the correct place to put it. All right. have to use my phone desktop is not loading properly. I think the Discord server is just freaking out. Okay, let me try to type again here. Nope, this time it's fine. I think it's just the Discord server, temporarily losing the ability to do text messages. Don't know why. It's on their side. All right, so everything is working now. Okay. So do we have any other questions about this particular program before we move on? Yeah. Would be okay to say the reg A is like a temporary box to hold the scalar to return as an analogy? Yes. Now, in this case, main is not making use of the return value at all. But if main wants to make use of the return value, main actually understands this is an agreement between the caller and the callee. So if main ever wants to do something with the return value from f, then you can just say that, main knows, okay, main knows reg A has the return value of calling f. There we go. Because it is an agreement between the caller and the callee in this case. There we go. So we got one more thing to talk about, which is what about parameters, right? Okay, so let's go ahead and make this program fancy. So when we say fancy, we are going to change the program. And this is a C program. Not that I'm going to run it because it's going to be a fairly simple program. So I'm going to specify x and specify y as the parameters. And then the return value of f, we'll just call it the sum of these two. And this time when we call f, we have to pass the two parameters. We can pass, let's say, 24 and 12. Okay, so the return value should be the sum of these two, which is 36. So the question now is, how do we do this? We know how to return the sum, but the question is, first of all, how do we pass arguments on the stack? Oh, I just answered my own question. I was originally trying to format it as a question, but then I answered the question in the question itself. Darn it. Okay, so we pass arguments on the stack. We do not use registers. The reason why we don't use registers to pass arguments is because there's a fixed number of registers. And depending on what architecture you're dealing with, that number can be really small, like the toy processor, right? So we only got 4 registers. One has a special purpose as a stack pointer, and that one can never ever be used, to pass arguments. Then we only have 3 registers that we can potentially use to pass arguments. What if you have 4 arguments? Then you are running out of registers, right? So we can't do that. Yes, we can definitely get a stack overflow, especially from bad recursive algorithms. But right now we are not concerned about stack overflow. Okay, so we are now just gonna be talking about how do we do exactly that, how to pass arguments to say to in this case. So we need to push the arguments on the stack. And the way we push the arguments on the stack is backwards, which means the second argument is pushed first, and then the first argument is pushed last. And those are all done before the return address is pushed on the stack. All right, so let's check out this code here. Okay, and this time, I'm gonna delete this line because that's not what it's gonna do anymore. And now we have to say, okay, based on what we just said earlier, we have to push first. And then we have to push 24 on the stack because we have to push the arguments before we push the return address. Now, the reason why we do this, okay, let me first explain why we are pushing the return address last. Because we still want to be consistent where at the entry point of the callee, in this case f, we want the stack pointer to point to a location where the return address is located. We want to maintain that. And as a result, we cannot push the return address first because that will change where we can find the return address on the stack. So we're still pushing the return address last because we still want, from the perspective of the callee, that whatever the stack pointer points to is the return address. So that's point number one. Point number two is, why are we pushing things in a reverse order? Well, part of that has to do with, if we do this in a reverse order, then the first argument would be right next to the return address. In other words, in the case where you have a variable number of arguments, we always know how to find the first one. There are situations where you can actually specify a variable number of arguments in C and C++. Not very usual, because we have other ways to do the same thing these days, but back in the earlier days before C++, this is it's very common that you would define a function where it can expect a variable number of arguments. All right, so let's look at it from the caller's perspective first. Okay, so push 12 is going to be decrement D. Okay, well, it's up to you. I mean, this is entirely up to you whether you want to initialize a register with the value that we're pushing first. So we can initialize it first. Decrement D, stda. So that would push a constant of 12 on the stack, and then we do about the same thing, dia with 24, decrement D, and stda. So now we're going to we have just pushed 24 on the stack. Yes, so Jonathan is correct. In this case, you can interchange the ordering between LDI and the decrement, and in this case, it would have no impact whatsoever, because we don't need to calculate the offset from an instruction to another instruction, and as a result, you can interchange these two, and it wouldn't make any difference. I would still suggest to individuals to stay with one particular way of doing things, so this way it would be easier to spot problems if you ever run into a problem, because consistency is kind of important if you want to kind of minimize the chances of putting a bug into the program. All right, so that's the easy part. Okay, from the caller's perspective, we just have to push the arguments one by one, starting with the last one, and then work our way to the first one. So we push the last argument first. So when you review these notes, you might want to write some instructions here, or comment it. So basically, we push the last argument first. All right. So the question now is, from the callee's perspective, how do we get back to these arguments? From the perspective of the callee, they're called parameters, not arguments, but kind of the same thing, right? Because it's like, okay, how do we get back to the value of 24? How do we get back to the value of 12? There are several ways to do it. Basically, they are on the stack, and you basically just want to say, well, we know that stuff is on the stack. We just have to find out where it is on the stack. And how do we get to those addresses on the stack? So those are the questions, okay? So to illustrate this particular code, it would be helpful to understand how the stack is organized before we get to the actual instructions to do it. But I have to be mindful of the time. We got about 15 minutes to explain this. So let's go back to Joplin. Okay, so in Joplin, I'm going to use the same kind of representation where each line item or each list item is representing the state of the stack. It is initially empty, and then just for the program that we are working with. So the first thing we push on the stack is going to be the last argument, which, okay, I'm just switching back so that you can see it. So the second argument is 12. Okay. So we have a 12 on the stack, and then we push the 24 on the stack, and then we push the return address to main on the stack. So I'm just going to use ret ADR to represent the return address. So these are the three items that we have just pushed on the stack, with the return address being pointed to by the stack pointer, because it is quote unquote at the top of the stack. So that means 24 as a value is at the location right next to the return address, and then 12 is the one right next to 24 in that specific order. Okay. Now the first thing we want to do here is not really to focus on how do we get back to the parameters from the perspective of the caller, maybe we should just run the code in the assembly code as is right now. In other words, we're not even bothering to do any computation and we just return right away. Because what we want to do is to use the trace analyzer to help us visualize and go like, okay, what is where on the stack? That would be a question to answer first. So let's go ahead and do that. So we're gonna get out of here, and then I'm gonna use my auto magical script here, and this one is called, what was the name of the assembly file? I cannot remember. It's not called red. This one, did I give it a name? Oh, okay. let me find out what name I saved this program under first. All right, so it's return value, I think. Yep. All right, so let's go ahead and run the script. There we go. And sometimes we can actually see it in action, like right now. And then when we get to analysis, it probably is done already. Yep, it is done. Okay. See, auto magical. So what we see here is this is the first push operation, is pushing 12 on the stack. 0C is the hexadecimal representation of 12. 18, which is 16 plus 8 is 24, and this is our return address. So by the time we get into the subroutine, which is at location 03, the stack pointer is pointing to exactly the return address, which is one thing that we talked about is we want to maintain that part of the agreement between the caller and the callee. But we also know that the first parameter is at the location right on top of the return address, and then parameter 2 is right on top of parameter 1 in that specific order. So that means if we want to get back to this location and also to this location, all we need is to say, okay, I'm going to use another register, make a copy of the stack pointer, and then just increment that particular register to where we need to go on the stack in order to retrieve the parameters. So so this is significant, okay? Because what the trace at this point is illustrating is consistent with what I typed in Joplin, except in Joplin there are no addresses associated with these particular items. We cannot really tell that return address is at location FD, the 24 is at location FE, and then the 24 is at location FE, and then the 12 is at location FF. But the trace analyzer is able to show us all of that kind of visually. Are we leaving stack pointer on in register D all the time? Yes, all the same and all the time. That's the one thing that register D is going to do, is it is always the stack pointer. Okay. All right, so now we are going to go back to the program. Okay, so we get back to the C program first so that we can track what we are trying to do. And then we switch back to the assembly code so that we can continue our implementation in assembly code. Okay, so what I usually do is I would show a map of what is on the stack. So I'm going to say Y is going to be here on the stack, X is going to be here on the stack, and then the return address is going to be here on the stack. And I have my own convention, meaning that what appears to be higher is actually at a higher address. What appears to be lower is at a lower address. And we also know, the stack pointer D is pointing to the return address at the entry point of F. All right, so we need to get to X, and then we need to get to Y. So what I can do now is to use a CPR. Okay, CPR is not a instruction that we have used before because we didn't have a use to use it. But what it does is it's just it's copying a register to another register. In this case, it's copying register D to register C. Remember, registers A, B, and C are kind of free to use. We can use any one of those three registers before we get to the end of a subroutine that has a return value. That's the only time when we have to say, oh, register A needs to specify the return value. But when you're doing the computation, all three registers are, they're usable. Okay, so now that we have register C pointing to the same location that register D is pointing to, I can now mess around with it. Okay, I wouldn't mess around with register D like what I just typed here, but I can mess around with register C because register C is not really the stack pointer. So I can do an increment C, which means at this point it is pointing to X. So I'm going to use a notation here to say that register C is the address of local variable X, or parameter X in this case, which is not exactly what I want because I want the value of parameter X. So I need an LD instruction here. So at this point, register A is going to be the value of parameter X. If I increment X one more time, excuse me, if I increment C one more time, it will become the address of parameter Y. And then I use another LD instruction so that I can retrieve that. So register B is now the value of parameter Y. So at this point, we have register A being parameter X, we have register B being parameter Y. Now we can perform the add instruction. So we're going to add AB instead of add BA, because this is handy, because if I add B to A, then the return value is already in register A, and we don't have to do a single thing to say, oh, by the way, the sum needs to go to register A in order to specify that's the return value. We don't have to say anything like that. So this is how we're going to do this. And what would we do if we had 4 parameters? Well, we get to each one of them individually, so hopefully you don't need to store all 4 parameters into the registers, because as you do the computation, some of the registers would not be useful anymore. And if you do need to get back to an earlier if you need to get back to a parameter that was stored earlier and you ran out of registers, sometimes you just have to redo it later on. So we're going to sacrifice some execution time when you run out of registers. But this is a very good point, Terence, because this is also why most modern architectures have more registers than the older architectures, because the more general purpose registers you have, the more you can stash values into the registers, so you don't have to go back to the stack and say, oh, I just forgot what was in what is parameter X. Can you get it to me? Can you get that back to me again? So you don't have to keep reloading the parameter into a register, because once you load it into a register, hey, you're good, because there are enough registers to store most of the parameters. So that's a good point to make. But a lot of architectures in the past, have very limited number of registers, and as a result, it is not unusual that you have to load a parameter into a register, do something with it, and then later on you have to reuse that register for something else, so that if you need to go back to the first parameter that you put into the register, a long time ago, you're going to have to do it again. It is inevitable, and this is also why the optimization of the use of registers is also is a huge topic in compilers. But we are not concerned about optimizing the performance of our programs. We just want our programs to basically be correct. So we don't have to optimize the use of registers in this class. But very good point. So I'm going to run the program again, and this time I want to see 36 in register A before the subroutine gets back to main. So it's all done here. Now we get back to the assembler, and we want to focus on register A to see what we are returning in register A. And this is the subroutine. F is starting at location 03. The last thing that we put into register A is at location 08, And if you go to the Assemble tab, you can actually find out what is at location 08. This is what is corresponding to location 08, and that is actually our add instruction to do the computation. It's adding the two parameters, to register A. So when we get back to the analysis, we can see that the value we are storing into register A is 24 in hexadecimal. That means we are looking at 2 times 16, which is 32, plus 4, which is 36. So we got the right value into register A. So you might think, oh, so Tech, we are all done here. We got 4 minutes to spare. No, we are not quite done yet. That's because, hey, by the time we get to the halt instruction, the stack pointer is not back to 00. We want the stack pointer to go back to 00 because that means we cleaned up everything on the stack. So the question now is, what is left over on the stack? Because I'm pretty sure the subroutine itself took care of the return address. So what do you think are still on the stack at location FE and also at location FF? The two arguments. Very good. Okay, so both Terence and Richard are correct that we still have those two arguments sitting on the stack. Do you think they're of any use at this point of the algorithm of the program? So let me go back to the assembly code first. So we are talking about after the subroutine returns, before the halt instruction here. So the question is, at this point in time, do we still need those two values on the stack now that the subroutine is all done? The answer is no, we don't need those anymore. Okay, so now here is another caller-callee agreement, which is basically saying even though the callee, the subroutine being called, is responsible to deallocate the return address, it is the caller that needs to deallocate the arguments. So the deallocation of the argument is not a pop operation, because a pop operation implies that those values are useful and I'm going to put it into some place. I'm moving data from the stack to a register. That would be a pop operation. In this case, I don't even care. Okay, I know there are two more items sitting on the stack. I don't need those anymore. So instead of using an LD instruction and then followed by increment D instruction, I don't bother with the LD because I don't need those things back anymore. So just increment, exactly. So that's why we have just increment over here, because we don't really care about what is at those locations. We just want to reclaim the space being used by those two items on the stack. So now we are done. Okay, so now we are done with this topic. So I'm going to rerun everything, and hopefully we'll see that the stack pointer is going to get back to 00. So we can actually keep an eye on this one as my script is doing stuff on the other side. Isn't that kind of cool? Unfortunately, the script is designed to only work with Linux at this point. Well, okay, to be more specific, it will work with Bash. Okay, you can actually install Bash and all the other utility programs that this script needs in Windows. But if you were to do that, you might actually be better off using WSL2 or some other way of using the script. Let's see. Okay, let me address those questions from the text channel. The first one is this why C++ doesn't have garbage collection? No, these are related to stack operations. Garbage collection relates to dynamically allocated memory. In other words, in C++, those would be the things that you allocate using the new operator, and then you would use delete to get rid of those items. In C, it'll be malloc, M-A-A-L-O-C, which is memory allocation, and free to correspond to delete. So those are dynamically allocated. They do not live on the stack at all. So, but to kind of extend my answer to Richard's question, C and C++ work with pointers, and pointers point to specific locations in memory, which basically means once you allocate a chunk of memory and you assign that address to a pointer, you cannot move it around. Okay, and because you cannot move things around after it is allocated, we cannot perform garbage collection. in other scripting languages like Java, okay, or Perl or Node, which is JavaScript, um, those do not use pointers. They use references. A reference is kind of like a two-way thing. Not only can you know where it's quote unquote pointing to, but that thing that you're pointing to also know that who is referring to it. So as a result, they can be moved around, okay? Because if you move one chunk of memory from one location to another location, you know exactly who you need to notify and say, by the way, I have moved and my new location is over here. That is why you can do garbage collection with most scripting languages because they do not use hard pointers. But with C and C++, because we use hard pointers, we cannot move things around, and as a result, we cannot do garbage collection. And without garbage collection, you can end up with a problem called memory fragmentation. Now, this is way beyond assembly language programming, but eventually you're going to run up to these topics in your C++ classes. So you can end up with memory fragmentation, which basically means you have chunks of memory being used within the heap, even though collectively you have a lot of space that is supposed to be not used, but because they're very small chunks interleaved with things that are actually in use, it is entirely possible that you can try to do another allocation of an object that is not really that big, but since it cannot fit into any of the free spaces between the gaps between memory regions that are actually in use, then your allocation would just fail. Even though you actually technically have enough memory, you just cannot find a chunk that is large enough for what you're trying to allocate. So that's called memory fragmentation. It is a concept that is somewhat unique to C and C++. All scripting languages usually do not run into that problem. And then Vlad asks, can't we overwrite the locations? Um, you mean the locations that we are freeing? Location FE and location FF? We have no use of those locations anymore. We are just cleaning up after ourselves after calling a subroutine. So that's it. Because I'm not really sure which location you're referring to, so I would assume that you're referring to location FE and location FF, which were used to store the arguments, but once the subroutine returns, we don't need those arguments to be sitting on the stack anymore. So what is the point of freeing them? Because it's good practice. Just because, okay, so let me illustrate what I mean by that. Now, just because this time there's nothing following f, the function call to f with 24 and 12, as the arguments, doesn't mean generally speaking we don't have anything following this, right? So if you have any code between the call to f and return 0, if you do not allocate those things from the stack, then you end up with two problems. One is you're wasting stack space, which is not a typical problem because you can say, I got 32 gigs on my gaming computer. What is 2 bytes, right? But the second problem is it also changes the offset to things that you need to get back to, okay? Because this is main, and in this case, main does not have its own parameters. But if main did have its own parameters, guess what? The offset to get back to those parameters have now changed because there are 2 extra items on the stack at this point. That is why we always clean up after we perform a function call. And this is also, I'm going to say this, even though I said I do not teach to the final exam. But in the final exam, you cannot make any assumptions of, oh, we don't need to clean up the stack because this is the very last operation. We always have to clean up after ourselves after we perform a function call. So it is not about whether in this particular instance is it going to cause a problem. It is about it's about the general approach. Okay, if this is a general approach and we're not at the end of the subroutine, is it going to cause a problem? So that's why we always have to clean up. All right, next question. We got a few items on the stack. I mean on the stack in the text channel. All right, so I think that decrementing just moved the pointer and then we will overwrite when we increment back to that location. So we decrement to allocate, everything that the stack pointer points to and all the locations um, on top of that are in use. Every location that is below where the stack pointer points to is free. So that is that. Return is top of the stack, which is kind of odd. It is technically the top of the stack, but it is also the lowest address of the stack that is being in use. And we don't want to mess with that, so we copy the stack pointer to register C and mess with the arguments. Yes. So, okay, so to explain this part, which is what Jonathan typed at 10:23, the reason why we don't mess around with the stack pointer, we don't increment the stack pointer to get to other items, is the stack pointer is a universal bookmark. Okay, look at it as a universal bookmark. Everything that the stack pointer points to and above are quote unquote protected. And you might say, protected from what? They are protected from gremlins. Yes, I did use the word gremlins. It's technical. It's protected from gremlins from changing memory locations behind your back. Yes, so there are these little gremlins, okay, in an actual program. They're just moving around, and the rule of engagement is anything that is below where the stack pointer points to, the gremlins can go and change the values of those locations whenever they feel like it. So that's why you don't want to change the stack pointer, because by incrementing the stack pointer, you are basically opening up memory locations for the gremlins in the background to change whenever they want to. So you want to keep the stack pointer until you know for certain that you have no use of those locations anymore. Yes, it is a very technical term, the gremlins. Awesome movie from the 90s, by the way. All right, so next question. Return is the top of the stack. Since we are not deleting the info, just moving that what is in register D. So yes, we're only moving the boundary. The boundary being which part of the stack is in use and which part of the stack is not in use. The part of the stack that is quote unquote not in use from your perspective, the gremlins can get to. But the part where the stack pointer points to and all the locations above it, they are quote unquote protected. So the gremlins cannot get to those locations. And by the way, for those of you who are curious about what gremlins are we talking about, they are interrupt surface routines. They are other things that can be happening in the background, signal handlers and all kinds of stuff like that. They're a little bit more advanced as topics, so we are not going to we're not going to get into those topics too much, but basically we make the assumption that everything below where the stack pointer points to can potentially be changed without your program knowing about it. So there we go. And then Jonathan said at 10:25, pretty sure the way you go through Discord messages is FIFO and not LIFO. It's random. It's actually random access. And then Matty said, I fixed what was for I have decrement and increment reversed. Yes, it is very common because it is counterintuitive, but that is for a reason why we grow the stack from high addresses down. There's a special reason for that, and it has to do with we like the ordering of things on the stack in a specific way. And Matt, Matt did a very good explanation of what gremlins are. Very good. Those are the bad ones. The good ones are fluffy. They're very nice. All right, so that should conclude today's lecture. And you guys can move on to the lab portion. The lab does have a passcode, if I remember correctly. So let me go check. And I can also publish today's Joplin notes. All right, so we are using the word frame as the access code for today's lab. There you go. So I'm going to type it in the text channel. Frame. There we go. So when you look into the code, or when you look into the questions of the lab, just so that people don't get started with the lab because they want to get started a little bit earlier. And also I can tell who was not in the lecture because those people would be asking me afterwards. It's like, what is the access to this lab? Even after I type it in Discord, some people still ask me. So when I'm just doing a quick scan of the lab today. Um, it is basically just related to what we talked about today. The arguments that we are pushing is just one single one. And for the most part, you probably want to utilize what was it? The trace analyzer. The trace analyzer can be helpful. And in question number 4, how we access a parameter, this is an alternative method to access the parameter. But effectively, you just have to understand where the parameter is located. Then you can use different ways to get to the parameter. So to answer this particular question in question number 4, you just have to don't try to replicate what I did in class, okay? And instead, try to picture what is on the stack and then look at the instructions already given to you, and then you ask backwards and say, okay, if this is how we're going to get to the parameter, what do I need to specify in register A in order for the other instructions to be able to get back to that particular parameter? Okay, so it is a problem solving kind of thing, but it's using the same concepts that we have been using in today's class in terms of what is where on the stack. You just have to figure out an alternative way to get to those parameters using the instructions that we have already introduced in this class. All right, so I think that is it. So I'm gonna go away for maybe 10 minutes and then I'll be back to answer questions. And depending on how much time I have, I might be able to finish posting the aggregated grades. And I'm gonna try to figure out a way so that you can tell how the points break down. Even though it's one single value that you see for a particular exam, because I found out that this class is too big. I cannot send everybody an email to tell you exactly how your score breaks down, which never happened before. I have had bigger classes and it didn't happen before. So somebody at the district level or Google changed some parameter, and now I have a problem sending email to all of you so that you can have a breakdown of, okay, this is why I'm getting that score, this is why I'm getting that score. So that's what I'll be doing, and you guys go ahead and work with the lab. I'm gonna sign out from the voice channel, and hopefully I'll see you guys on Thursday.